mapping the slits to the sky. So this is a feature request and something that also I was also interested in. And just to give a bit of background real quick, so this is to produce images like this, so you can actually see where your slits are on the object. You can see this in APT, but this is a way to export it so you can see it for yourself and make figures like this. And just to show, so the MSA shutters look something like this, and there are these bars, in between each shutter where the light doesn't come through. So here we're showing the red area is where you get light coming through. This particular source was sort of just on the edge. And if there were a point source, you would have lost a lot of the light from it. You might have just gotten it in there. Fortunately, this is an extended source, and this is one of the ERO press release the galaxies here. So we were fortunate to get that light in there. If we compare what we see in APT, it's very similar, but it does show the full extent of the slit. So some of that is, the bar is going to be blocking. And if we go back and forth here, we can see that I've managed to map these pretty well, where it looks like they're almost exactly aligned. All right, so this is what this notebook is going to do, and it took a little bit of work to figure out, but now you'll see it's not too bad once we know how to do it. All right, so we're going to stick with the ERO program, G395 observations, and we'll do this galaxy and also a few others. We'll show these extractions, and so we're going to to show these images here. What we're going to do is we're going to I downloaded data from the Dawn JWST archive, the DJA. So this is their F200 reduction. I also downloaded the other short wavelength near-cam images and combined them into a color image that I'll use here. I show an option to just use a single filter image, so you could do it either way. But here I'm going to go ahead and use the color image. And we're going to show how to map these onto the sky and back. So we import some libraries, including the helpful data models and AstroPy, and a few other plotting functions. And then for the color image, we're going to need the Python image library. All right, a few helper functions here, including this useful one to filter the table, download JWST files from MAST, and to download these large files, the near-cam images, some helper functions that'll give us a progress bar. I think each of these took like a minute to download, so you might be able to run this in real time as we go here. All right, here I think we're actually going to start out with a different source. This is the higher redshift one in this in the ERO observations, the 8.5 redshift. Now we'll define our data directory, and I already know the file name, so I've just put it here, and it'll pick that source ID and put it into the file name, and it'll download that from MAST. And so I'm going to download the S2D and also the X1D extraction, just as they are in MAST. If you want to improve on those, check out the first notebook. So now we're going to load those into the data models. One thing to mention about the S2D data products, if they come out of Spec 2, they're going to be for that one detector, and they're going to have all the sources for that one detector. If they're from Spec 3, they're going to be from one source, and they're going to have all the, well, they're all going to be combined into that final reduced product. And so this can handle it either way. And then I could mention if it's a CAL file, then it'll have all the detectors separately, just sort of reorganized. But either way you have it, it's going to go ahead and download that and, load in the data. And we'll have the 1D loaded as well. So one of the questions a lot of folks ask is, how do I get the wavelengths in the S2D file? There's a way to do it, as I'll show below, but usually I just take the wavelengths from the X1D because they're on the same wavelength grid. So here I just show once we download this into the data model, they just come out this way here. Or if you're using fits to open it, it'll do the same thing. But the other way to do it is to get it from the S2D. And there are these different coordinate transformations that I'll actually show here. I made a slide to demonstrate this because it's there's a lot going on here. So there's in the data model, there's actually these WCS coordinate systems and the transformations between them that can handle. So there's more than three, but I just showed three here that we're going to need. The first one is in the detector. Well, this is the reduced, the S2D rectified. So you have the X going in wavelength. So it knows how to map that to wavelength. And then vertically, it maps to a straight line, basically. So we show that here in the world coordinates. And then there's also the slit frame. So it tells you where you are within the slit. So this gets to the question from the previous notebook about where are you in the slit frame, and this is how you can figure out where you are with these different coordinate systems transformations. There's also in the MSA Metafile, the coordinate system is different. So I guess for historical reasons. So you actually need to convert between these two different coordinate systems, and I'll show how to do that in the notebook too. So we're going to download our MSA Metafile, and I showed in a previous notebook a lot of the details of this. Here we're just going to download it. Again, we'll show these are the four extensions that are in there, and we're going to load in the shutter table and the source table. And just briefly show that there's two configurations in here, and there's also three dithers. So this is going to help us show the slits on the sky. You can actually see over here there's the three slitlets, and then there's the dither to either side when you're doing the nods for the background subtraction. And here I'm just showing all the different sources that are in here. These are the science targets, and then these are the empty slitlets for that can be used for background subtraction, as Kaylee will show. So here we're just going to show that particular source and the array and deck. And here they are again. If you want to extract them, that's how to do that. And then just to show, these are the now within the shutter table, you can see where that source is. It's in this row and this column, and at least for the first dither, the middle one is the primary source. That's how the MOS observations work. It's always in the center in that first, and then it goes up and down. And so, right, that's just saying that the first one is where we have our primary source, the first dither. All right, so now we're going to download this color image that I made, and so I posted it here, and you can go ahead and download that. And then also from the DJA, we're going to download the F200 fits image near cam reduction. So, and then just to show a little bit about the near cam image, here's the WCS that's in there. We also need that to map things to the sky. Here's our color image that we're going to use. There's also an option to not use it, just use a single image. All right, so these are the slit sizes, as I mentioned over here, 0.46 by 0.2, and then the bar widths are 0.07 arc seconds. And all right, so these are the different coordinate transformations that I show over here between the MSA Metafile and the S2D WCS. So this is just how to do those transformations. One is in the open slit frame, and one is in the full slit, including the bar. So I show how to convert between there. And then since we have the three dithers, I've taken those various rows, and I see how much you need to shift in each direction to be able to show this fully. And all right, so now let me show you where we're going with this. But before I show exactly what it is. So here now, because I have to calculate some offsets. Here's the final version. All right, so this is showing the slits and also the full region with the source here. But it was a bit tricky to get here. So the S2D WCS is actually a bit off, not by much, but so what we do is if we just plot it directly, we get this gray region over here, and then we take that here. Maybe I can zoom in a bit. Maybe not. There we go. We take that, and then we also use the estimated source position within that slit, the X and Y, and we map that back to the sky as well. Then we're going to compare that to the actual input catalog RAN deck, which is over here. So there's a bit of an offset, and we're going to use that to correct the positions of these slits that I'd drawn in gray over to the red regions, which we believe are correct. These are as were defined or commanded by APT. These observations, we don't have any better information on where that is currently. But these have to be pretty precise, these pointings, in order to make sure the objects are within the slits. So we're correcting this and using the, so this is, similar to what you'll see in APT, as I showed before. So if I back up here, these are these offsets here. So it's off by 1 pixel in the X direction and 2 pixels in the Y direction, where these are, I forget, maybe they're either 0.02 or 0.04 arc seconds. And all right, that's the correction. And then now I'll show this again, the full S2D. So this is great if you want to map the slits onto the sky. Now we're going to map the sky back to the slits and the S2D. So now we're going to do this part of it here. So the full S2D, we're going to map to the sky. And so this is also encoded in these WCS transformations. So this is the full extent of it on the sky, where things have been extracted from. And then I have, now I take the image and I resample it and back to this at a high sampling rate, back to this rotated frame now. And these are the 5 dithers, or the 5 slits we're going to show, including the dithers. And here they are rotated back. So now they're aligned in the same orientation as your S2D. And putting it all together, I borrow the functions I have from the previous notebook, and now I can show the map slits alongside the S2D and the X1D. I didn't try to do them exactly over here to be a lot smaller, but you can see where now you can see where things are coming from in the S2D, more or less. And here I'll just do a few more sources just to demonstrate. Here's our friend with the 5 slitlets that you can see alongside the S2D and the X1D. Again, this is straight from mass. This one gets a bit confused, and we showed how to improve this in the other notebook. And here's a few more. There's this one at redshift 7.7, and then a lower redshift one where you actually see it filling the whole slitlet and then some. So now you can see which parts of the galaxy are actually included in the slit or not.